Hey, hello. Thanks for inviting us. This is the first point. Nice to meet you all. We'll start. We're not sure who is with us today, so let us maybe introduce ourselves.
Hey, so as Piotr said, I'm Michał. I'm an engineering manager in the GKE AI training team. So that team is based in Krakow, and we are basically working with all of our users and customers who want to perform AI training on our Google Cloud.
Yes, and I'm tech leader in the Cloud Composer team. We'll tell more about both products that we support. And we not only I have this cool Halloween costume on me, we also embedded very carefully some generated pictures that blends Google and Halloween theme to make it more appropriate for the event. So look on our slides for those small Halloween artifacts. So this is the plan. I work in Cloud Composer team, which is managed Airflow. How many of you heard or used Airflow before, Apache Airflow? Some here, perfect. Because we have the presentation is built like we talk about the basic, but we also have some more complicated stuff.
Okay, and who has ever used Kubernetes before?
Cool. Okay, so to start with, we are not ML engineers. We have to confess that. We work on those two cloud products, which has also their open source phase. But both can be used really well to orchestrate ML workloads. Both can be used together, and this is what we prepared and what we want to talk about for the conference, Airflow conference that took place this year in San Francisco. We prepared the example workflow of simple fine-tuning, and we want to show it here as well. So let's kick it off. Let's start with Cloud Composer. You can see the first Halloween theme there. So why orchestration matters? This is the first question from me. So over the time, data engineers and ML engineers need to face the challenge of learning different processes, workflows, and different tools across different environments. When they switch the jobs, they have to also learn a new stack. Also, the complexity of MLOps is increasing, and the pipelines that are used needs to be testable, repeatable, easy to debug, and also easy to monitor. And the last thing, everyone is using notebooks, but we rely on them too much, and they require a lot of human intervention, so we want to automatize whatever we can. So what comes here is Apache Airflow, which is the open source orchestrator written in Python, which became I think it was started in 2014 or 15 in Airbnb. It was open source 2 years later, I think. And it became de facto a standard tool for data pipeline orchestration. It allows you to write in Python super complicated workflows, which then can run either on your on-prem Airflow installation or in one of the cloud installation of Airflow, for example, Cloud Composer, which is the product that I'm leading, which has team in Krakow, but mostly in Warsaw. And what we do, we manage Airflow service in the Google Cloud. So we provide you the tool to easily deploy, create Airflow cluster, and focus on the things that you want to focus, so writing your orchestration in scale. We also provide a lot of connectors to different GCP services, and Airflow itself provides tons of integrations with other things that help you run stuff. Cool. So some of the features of Cloud Composer that we built on top of the Airflow, because we deployed on the Kubernetes clusters, we natively support autoscaling. This is a nice feature and a nice addition. We implemented autoscaling that is watching on the tasks in the queue, and whenever workers needs to be added, you can configure it on top of the environment, and the new worker is spawned. I wanted also to show you some of the controls. So you can see there is a lot of configuration options where you can create your Airflow installation. And there is very nice monitoring plane where we basically show all the stats and information from Airflow, so we can easily see and monitor the workers, your DAGs, your tasks. And for this presentation, for the DAG that we prepared, we need basically 3 or 4 Airflow concepts. So first is DAG, which is directed acyclic graph, which is the term that is used in Airflow to speak about workflow. So workflow is a set of tasks that forms a DAG and are executed then by the Airflow itself. Task is a basic unit of execution. Underneath you can see very simple DAG that also creates very simple tasks, which will print hello world. So we have DAGs, we have tasks, and the last thing is operator. Operator is a template for the task, which is pre-provided and allows you to easily write pipelines and focus on the orchestration rather than producing a lot of Python code. There is bash operator, Python operator. In fact, there are, I think, more than 1,000 easy to use off-the-shelf operator provided by the community and Google itself. We own as a team, we own Google operators to connect with and integrate with different GCP services. And underneath there is another piece of code using HTTP and email operator to give you a sense of what I'm talking about. Yeah, Google Cloud operators, those are things that we support, that we contribute to community, open source community, so that everyone can use both Composer, but also standalone Airflow for the orchestration. So the orchestration part is over.
Okay, so I'm taking over. Okay, cool. So let me actually ask one more question. So who's ever trained or fine-tuned an LLM before? Okay, not a lot of people, but you've all probably heard that it's a very resource-intensive thing that you actually need to have hundreds or thousands or tens of thousands of GPUs to actually create something. And those GPUs are a very scarce resource. As you probably know, no one has enough of them. Even big cloud providers cannot buy enough of them. So when a big company actually buys or reserves a lot of GPUs, they need to share them between their own organizations or teams. They need to prioritize them, and they need to prioritize their usage, the workloads that run on those GPUs. And there are many manual ways to do it, using spreadsheets or using some time tracking, but that's not efficient enough. So that's why a lot of those resources, those GPUs, are often becoming part of a dynamic infrastructure instead of a static one. So in the past, you would have an enormous cluster with a static pool of machines. Those machines would have static resources. But now, because we suddenly need to share, there are, at this scale, there's a lot of failures. We need to somehow move resources from one pool to another. The resources are not homogeneous, but are heterogeneous. That's one of the reasons why Kubernetes was created. So not a lot of people know that, but Kubernetes was actually created with some of the concepts from our planetary cluster management system called Borg. And the goal of Kubernetes is to basically abstract whatever infrastructure you might have into something with an interface to easily run your applications. Okay, so less than 50% raised their hands when I asked about Kubernetes. So let me just quickly say how Kubernetes works. So in Kubernetes, there's a control plane which manages the entire cluster and which the workers talk to. Then there's an API server to interact with it using clients. There's a scheduler, which is responsible for scheduling your applications to resources. And then within Kubernetes, there are containers, as you know them, pods, which are a group of containers with the same purpose. Usually it's just one container per pod, but it can be multiple if they need to work together. Then there are deployments, which basically manage those pods, and then there are jobs, and that's in machine learning, like that's the usual entity that we use. So just a short list of how it looks like in Kubernetes. There's a collection of pods which right now are running. They are not restarting. They are healthy. Pods are grouped within namespaces, and within a pod you get like either one or several containers, as I said. Okay, so why people should use Kubernetes? So one of my responsibilities as being a member of the GKE AI training team is to make Kubernetes the best place to run your AI workloads, especially AI training. And it's actually a very easy job, because Kubernetes itself is great, because it comes with a huge ecosystem and the community. It has a very good understanding of the infrastructure. It knows how to scale itself. It knows how to self-heal, and that's why we don't need to care so much about those basic features of Kubernetes, and we can kind of make it like into a super specialized place to run AI training workloads. Okay, so a small intro into what my team is specifically working on. So we work on a thing called Kueue, spelled with a K. And it's a cloud-native job queuing, admission gatekeeping, and scheduling. So how to translate that sentence into like a real use case? So imagine that you have 5,000 GPUs, funded by 5 departments. There are tens of researchers, tens of teams. There are thousands of GPU hours to manage, and they need to be managed at capacity. Something needs to decide who should run which workloads at any given moment. And that's what Kueue does. So basically, on this very simple picture, you can see team A and team B. They have very different jobs. So now they enter Kueue, and Kueue analyzes those jobs, and it decides how those jobs should be queued and allowed access to resources. And if you've ever competed in Kaggle, you might know this person. It's a former colleague of mine, and Philip here is basically saying that one of the biggest challenges in AI and ML at the moment is to actually use those very expensive and scarce GPU hours in a very optimal way. So that's kind of the problem that we're trying to solve. Okay, so let's see how both Airflow and Kueue can work together. So let me introduce like our example that Piotr and I worked on. So we have a very simple LLM fine-tuning example where we start with raw data. We like usually during like an experimentation phase, you might want to apply different methods, different parameters to that raw data to see what actually gives you the best results. So you might end up with like multiple versions of the same training data. Then you want to run your LLM trainings or fine-tunings. First, you might not want to run like your hero job immediately. So you start again with different data sets, different parameters, and at the end you get different models. Then you might want to store those models and deploy them and compare, benchmark, test. And this is what we did with Piotr.
Yeah, maybe let's come back to the previous slide and say how we translated it because we run it on Cloud Composer. We express it as an Airflow DAG, and we also used Google Cloud services to make it work seamlessly. So we started with the raw data, as Michał was interrupting me if I say something wrong. We put it on the cloud storage. With the Airflow itself, we created the GKE cluster dynamically, in which we installed the queue, so the GKE job orchestrator. Then, using the queue from the cloud storage, we synchronize all the data to the jobs, and we started to run first pre-processing of the data in the GKE jobs, and then the long fine-tuning jobs, which, what you will be able to see on the demo, will run on dynamic pool of resources, which is scaling itself. So after that, there is one simple benchmark. We store again to the cloud storage the result model, the one that, based on benchmark, was fine-tuned in the best way. And as the last step here, we deploy it to the VertexAI service. So this is the service provided also by Google, where you can run, deploy, test your models, operate. I use a lot of the models that are easy to use. So we end up with the endpoint on the VertexAI where the model is stored, and we clean up after ourselves. And this is all expressed in one Airflow DAG that you can basically click and run. Yeah, so to give you sneak peek to a DAG, you probably are not able to see it very well, but this is pieces of code which consist of this Python operator. This one is starting the queue job. So you can see how you can provide different resource requirements for the fine-tuning job, how you connect it with SA, provide different parameters to that. I think it will be better if you go to this is the GitHub repo that we prepared for the Airflow conference, and you can see the full example there. It also contains different information about the steps that was shown on the graph. If we have time, maybe we can look at the code, but it's not that important. We also have a demo of this process runs for, I think, 3 hours, but we speed it up. Do we want to run it now or go to the... Okay, let's run it. Let's see if it works. Okay, cool. So you can see this is Airflow UI, where you can see the entire graph. So the same representation of what you saw on this nice picture, but represented as the steps of jobs. We create GKE cluster first, and then we install and set up the queue. Then here we install custom resources of the queue, which Michał will talk later, and we start the fine-tuning LLM pre-processing and then fine-tuning job. At the end, we pull it together with benchmark, which benchmarks all the models together, and we deploy the model to the VertexAI. And now, not on live because this is video, but the example how it works. On the 3 canines consoles, you can see resources that are provisioned, nodes in order to present the auto-scaling that's happening during fine-tuning, and the jobs here. So you can see the GKE cluster was created, all the queue resources was run, and now the queue jobs are admitted. First, the processing jobs are finishing, and now those heavy fine-tuning jobs get admitted to queue. And as you can see, the node pool is dynamically provisioning new nodes to support the resources that we provided in the example in the configuration YAM. And the fine processing is happening, and it finishes with the benchmark, which is used to select the best model. it happens. As you can see, the time flies really fast here. And after the benchmarks, the model is getting deployed to the Vertex, and the GKE cluster underneath is getting deleted. Yeah. So this is end-to-end scenario of the very simple fine-tuning that you can do using different services. Oh, and here you can see the VertexAI in an actual model that is deployed. Yep. And if you want to use QR code to see the code of this DAG, it's not like the only thing that you can do in Airflow, of course, but those are the operators that we created specifically for GKE Kueue to support such massive GKE workloads.
Cool. So let me share with you like some of the advanced features of Kueue and how our users use it to efficiently use the infrastructure that they have. So there are actually more features than that, but I'm gonna be telling you about priorities, borrowing, preemption, and topology-aware scheduling. So when it comes with priorities, if you don't set priorities for your workloads, Kueue works as a simple FIFO. So whoever gets there first is going to get their job admitted. And you can define priorities using weights, and then you can use those priority classes. So you effectively you get a priority queue instead of a FIFO queue. Okay, one of in my opinion, the coolest features of Kueue is borrowing. So if you have different divisions within an organizations and they receive different funding, they own their own pool of resources. As an organization, you never want to waste those resources. So if they are available in Kueue, there's an option to actually borrow those resources to or from another team. So for every resource, you can actually configure like how much of that resource you can borrow or lend. And then if you borrow those resources, if you want to get them back again, but they are occupied, like they were borrowed, so they came with no guarantee that someone might use them indefinitely. So here comes preemption, and in Kueue we can actually preempt many different things. We can preempt jobs on borrowed resources. We can preempt jobs that are lower quality, or we can even, if we have like a super important job, we can preempt and borrow at the same time. So Kueue will actually try to preempt everything that's lower priority and try to borrow as much as possible to run this very important job. Okay, so let me go through like a super quick scenario of that. So let's say that we have team A and B who have their own resources, and then we have team C who also has their resources. And team A submits a job, but they don't have enough quota to run this job. So in Kueue sees that team C, which allows borrowing, that team has enough resources, so it borrows those resources to team A. But now, after some time, team C wants to submit their own job, and Kueue checks the queue for team C. They see that some of the resources are borrowed or lent to other team, and there are not enough resources to actually run the job for team C. So what Kueue will do is it'll preempt that job of team A. Team C's job will be run, and then team A's job will be queued again. And one final thing, which is nowadays, which is super important, it's like the freshest of the fresh thing that we've been working on, is topology-aware scheduling, which basically allows the Kubernetes scheduler and Kueue to work together to find the best set of machines as close together as possible to minimize network latency and I/O latency in general between the workers. Okay, so let me super quickly run through like basically an image description of what I just showed you. So let's say that we have two teams. We have team with low priority jobs. So those jobs get admitted using the reservation and the spot pool. And then we have another team who comes with a higher priority job. So one job gets admitted almost immediately. And for the other job, there's not enough resources. But Team B actually borrowed some of the resources from Team A. So one of their jobs will be preempted, requeued, and that way Team A's job can complete. And Q can actually realize that it can add like another spot machine that was allowed. So it did that. Cool, that's everything.
Thank you very much. We made it on time. Do we still have 1 or 2 minutes for questions? Not really. Okay, cool. 2 questions.
So when I think about ML workloads, my first reaction is VertexAI pipelines. How is it different from what I can do with Composer? One question, and the second one would be, what is the cost of fine-tuning? Can you give us a range?
So the second one Michał will take. And the first one, this is like the good observation. Vertex provides pipelines. They're much simpler than you can get from the Airflow. So we as Google Cloud, I think, provides 4 or 5 different ways to orchestrate. So basically run different things after each other. And the Cloud Composer is the most rich one. So basically, because it is Python code, you can express anything that you want. And it is also the most reusable one. So it provides, because this is the open source, and everything that you run on Cloud Composer, you can also take and run everywhere on the Airflow. And so how we position ourselves in the cloud orchestration tooling is that for the users that needs to want to have exit strategy for their workflows, and have very complicated workflows made of different parameters and scenarios, Cloud Composer is for them. And Vertex is very specific for ML also. So it allows you to do simple things. What we have a lot of Vertex operators. So what we are seeing people are doing is they are using Composer for the high-level orchestration. For example, take this file, put it here, use it, ingest the data there. And then they invoke, for example, Vertex pipeline specifically for the Vertex part.
Yeah. And when it comes to the cost of fine-tuning, like it's supposed to be orders of magnitude lower than training your own foundational model. So I would say, it depends. It completely depends on the data. But to give some estimates, I would say that fine-tuning is supposed to be thousands of dollars or tens of thousands of dollars, and creating your own foundational model is hundreds of thousands of dollars to millions and billions of dollars. So, yeah.
Okay, I have more like a fundamental question, why Q and not extending autoscaler with more capabilities to share resources? I'm just curious if you have an answer for this.
But do you have a very specific autoscaler in mind, or?
Kubernetes autoscaler, in principle. I know that the way I use it, I use it with scaling on CPU or memory. I'm not sure if it's easy to scale it on GPU, but I presume that it's possible to extend it that way. So I'm curious, because I was looking at Q for non-GPU related workflows. And to be honest, I was put off with the complexity of this, and I thought, well, I can build my system just using regular autoscaler, and honestly, it works just fine. And now, after this presentation, I see that there are more capabilities like preemption and things like that. But fundamentally, I think that this could be also solved with autoscaler, and just wondering why Q is better than reusing existing abstractions.
Yeah, it's a very good question, and it's a question that the Kubernetes community is actually discussing very eagerly at the moment. So there's at the moment in those discussions we call this particular topic a scheduling triangle, where you have basically three pillars in this triangle. You have scheduling itself, you have autoscaling, and you have admission gatekeeping, which is basically queue, and admission gatekeeping and preemptions. And you have three components which have like a single goal to run your jobs and to make sure that they run efficiently. What queue does, in addition to like all the features that I've mentioned, in addition to like a simple autoscaler, is that queue is actually queue can be run together with cluster autoscaler, which is a Kubernetes project which was originally created at Google and now is owned by the Kubernetes community. And the cluster autoscaler can actually talk to cloud providers, and it can learn about the quota from like the cloud providers like customer accounts. So if for example, your organization has a quota to use like 1,000 GPUs, like if you use like a single autoscaler, like you would scale up and scale up and scale up and scale up. If you set like your scaling metric to be like CPU usage or RAM or GPUs or whatever, you will like iteratively scale up. And here, what you're getting is your account queue doesn't become aware of your account, but queue can talk to the cluster autoscaler, and they both can figure out the optimal way to use resources by your organizations to run those jobs. And also one more thing about queue, which I didn't mention, is that specifically for AI jobs and for LLM training jobs, queue has a feature called gang scheduling, which is not supported by the standard Kubernetes scheduler, which basically says, I want 10,000 workers right here, right now, and it's all or nothing. So normally, like those jobs would scale up, and you would wait for resources with standard autoscaler, but all the workers would be idle, and all the resources would be wasted until you get to 10,000, and that can even cause deadlocks if you have multiple teams trying to achieve that. But with queue, you say, I want 10,000, and queue will wait with admitting that job until it can see that it can get 10,000 GPUs.
Thank you very much. Thanks.